That's visible. Now walk back here. Everybody see that? If you can't see it, I mean, feel free to move up. Again, these notes are on Canvas too, under the week 1 module. Okay, so I think, oh, oops, admit. There we go. All right, so is this video being recorded? Yes, this video is being recorded. All right, so welcome to day 3 of calculus. Today's where the action really starts. Because today we're going to talk about limits, like the most fundamental concept in this class. Okay, so if you want to sleep every other day, that's fine. But today you have to pay attention and you have to get it. Okay, so before we start, I do know that I forgot to talk about perpendicular lines on Tuesday. So I'm going to talk about that today really quick. Not very hard, and it's not going to come up very often in this class, but it is useful to know. So as a reminder, you have homework due on Monday. It should all be review. If you have any questions, though, come see me. I'm in my office all day, most days, unless I'm teaching. So you can always just drop in with a mask. And oh, everybody's got their green passes, right? Do I have to go around and check everybody? All right, I believe you. All right, so if you have any questions, come see me. You can email me. You can always request the Zoom session. You know, whatever method you want, I'm here to help, okay? I say it right here. I'm going to use my laser pointer. I'm here to help. Amazing. All right, so I forgot to mention perpendicular lines last time. Perpendicular lines are simply lines that meet at a right angle, okay? That definition is not very helpful for the homework. The way that you know two lines are perpendicular is if you take the slope of one line and you multiply that by the slope of the other line and you get -1, okay? That's how you check to see if two lines are perpendicular. That's all there is to it. Why -1? Well, I mean, I could show you. It's not very illuminating. It's just a little bit of trickery. I think it's easiest to just remember two lines are perpendicular if you multiply their slopes and you get -1. So as an example of two perpendicular lines, if you have the line y equals 2x minus 17 and y equals -1/2 x, plus 20.45, these lines are perpendicular because if I take the slope of the first one, 2, and I multiply by the slope of the second one, -1/2, I get -1, right? So that's how you check to see if these lines are perpendicular. The intercept does not matter, okay? The y-intercept has no effect on if two lines are perpendicular. Now, there is one special case. Let's say you're looking at the line y equals, my palm always makes me move the screen, so I have this little towel to keep that from happening. Let's say you have the line y equals 1. Well, what slope does this have? The line y equals 1. Careful. The slope is what's in front of the x, right? Is there any x happening here? So what is in front of the x? It's 0, right? The slope here is 0. Where'd my towel go? The slope here is 0. So this is really 1 plus 0 times x. Well, now it doesn't make sense that I would multiply this by anything, this slope by anything, and get -1. So the one case that you need to be careful about is horizontal and vertical lines. So y equals 1 is a horizontal line, right? It goes through the y-axis at 1, and to get your next point, to use the slope, you go up 0 and over 1. So that's a horizontal line. So any line that's perpendicular to this, we would say the slope is undefined. And it's just any line that looks like x equals any old number. So x equals 4, for instance, is perpendicular to y equals 1. Okay, so any two lines that look like y equals some constant and x equals some constant, those two lines have to be perpendicular. That's the only special case to consider. Okay. Are there any questions about perpendicular lines before we get started on the good stuff? Questions. Okay, so let's get started on, oh, I mentioned this already. We're not going to talk much about perpendicular lines other than this review. They might come up a little bit, but it's not going to be like a key focus of the class. Okay, so let's start talking about limits. So let's say you go for a run. I hate running, but I try to do it every so often. And you track how far you've gone on your run using your generic GPS. Okay, no, I'm not using any brand names, so don't come after me for money. All right. So it keeps tracks of how many miles you've run in how many minutes. Okay. So you want to know how fast. You feel like at about 10 minutes. You're going down this hill, you were really booking it. And you want to know exactly how fast you were going. Okay, so, but all you've been given is your distance and time data. So here's what this data looks like. You look at your phone, your generic phone, non-branded phone, and you get this data. At 0 minutes, you obviously had run 0 miles. 1 minute you ran 0.08 miles, and so on and so on. That's how this table works. Okay, so at 10 minutes you would run 1.15 miles. The question I have for you is, how could you use this data here to estimate how fast you were running at exactly 10 minutes? At the moment you hit 1.15 miles, how fast were you going? Do we have any guesses about how we would use this data to do that? Yeah, exactly. That's the whole idea, is we want to find the slope at 10 minutes, right? And this is kind of the key idea of at least the first half of calculus, is I want to find, if I have a straight line, it's easy to find the slope, right? If I have a curvy line, so I mean, my distance is doing something like that. If I have a curvy line, and I want to know, well, what was my slope here? And here, slope really means speed. Well, it's going to look something like that. We're going to get more into that. But today, we're just going to talk about, so ignore this. We don't want this. This might confuse more people than it helps. Today, we're going to talk about just how can I estimate? And slope is the exact right answer. So what would be a first guess at how fast you went at 10 minutes? Well, what was your average speed over the first 10 minutes? How would you find that? Yeah, exactly. Average speed is just the distance you traveled divided by the time it took, right? And average anything, I mean, this is in miles per minute, really, right? So that tells me how I'm going to calculate this. So my first guess is just I'm going to use the average speed I had over that first 10 minutes. Well, I went 1.15 miles. I started at 0 miles. And it took me 10 minutes, right? And this is 0.115 miles per minute, which if you calculate that, how did I get this into miles per hour? I multiply by 60. So 0.115, oops, that was awful handwriting. 0.115 times 60 equals, well, I'm gonna do this in my head mentally. All the people on Zoom are gonna be amazed at my mental math abilities. Just let me really crunch the numbers really quick. I'm really crunching them. And that comes out to be 6.9 miles per hour. MPH. Okay, so that's not a bad guess at what our actual speed was, but what would be a better guess from this data here? That was at our average speed over a 10-minute interval, right? What would maybe be, I mean, my speed at the start of the run maybe didn't really affect the speed 10 minutes into the run, right? But what other information might I be able to use to get a better guess at my speed? I mean, another way to think of it is like we've only used this bit of information and that bit of information, right? Look how much more information there is on this table. So what other information would you like to use from this? We could take our average speed over just that minute before the 10-minute mark, right? Does that make sense to everybody? That would probably give me a much better guess at how fast I was running at the instant I hit 10 minutes. Does that make sense? Okay, so I'm going to use this line and this line to calculate maybe a better guess at my speed. It's still an average speed because I'm just dividing miles by minutes. So that's just going to give me miles per minute. And so when I do that, I'm going to get 0.15. Well, I'll write it out. Sorry. I'm going to get 1.15 minus 1.0 divided by 10 minus 9 is 0.15 miles per minute. And when you multiply this by 60 to get into miles per hour, this gives you 9 miles per hour. I did that one beforehand. I'm not. I am a genius. Actually, it's not that bad. Okay. Is everybody clear on why I did that, first of all, and then the actual mechanics of it? Okay. Well, then you remember that the US government is tracking your movements at an even smaller time scale. This is a joke, but also probably true. So you remember that the US government's probably tracking your movements to like the 100th of a minute. So then the table you get when you want to use that data is right here. So here, if I'm tracking to the 100th of a minute, I ask the government for this data and they say, sure, we don't mind. Then now I can calculate even better averages, right? Or even averages that will definitely be even closer to my true speed at 10 minutes. Because now I can use really any two lines. I'm going to jump straight ahead to using the closest two time intervals because that's probably going to give us our best guess, right? Is that clear to everybody? So when I do that, I'm going to get 1.1485 minus 1.1470 divided by 10 minus 9.99, and this is in miles per minute. Well, when you do that subtraction, you're going to get 0.0015 divided by 0.001 miles per minute. So, I mean, I can move that over to, right? Oh, did I mess something up? Oh, sorry, that should be right there, right? Oops, sorry. There we go. Give me that. 0.01. There we go. Much better. All right, so move that over. Sorry about that, everybody. But you move both the decimal places over. I get 0.15 miles per minute, again, just like last time. And so that tells me that I'm running at 9 miles per hour. And again, this is an average speed, but it's an average speed over the last 0.01 minutes before 10 minutes. So when I took my average, and actually when you take the average speed over all of these intervals, if you did the same calculation over the time interval 9.95 minutes to 10 minutes, you still get 9 miles an hour. You get that for all of these intervals. So what do we think is our speed at 10 minutes? Anybody have a guess? A wild guess? If I take my average speed over these shorter and shorter time intervals, it's getting closer and closer to, or I mean, really, it's staying at what number? 9, right? This is the whole idea of a limit. I never actually said what my speed was at 10 minutes. I said, look at what happens as we get closer and closer to 10 minutes, right? So as these intervals get closer and closer to just looking at the value of 10 minutes, the average speeds are getting closer and closer to 9 miles per hour, right? So that is really the whole idea behind a limit. We want to look at something not at a value, which is what you're used to doing. In every math class before this, if you were looking at a graph or something, you cared about what is the function value at this point. In calculus, we don't really care about that anymore. We care about what's happening very, very close to a point, but not necessarily equal to that point. Okay? So the limit, again, it's like the fundamental idea behind everything we do. We're not going to, for the first couple of weeks, we're going to be in the nitty gritty of actually, thank you, John. In the first couple of weeks, we're going to be in the nitty gritty of actually calculating limits. Later, we're going to learn rules to help us calculate them easier. But everything in calculus that we do, when you really look at it, is a limit. Okay, so this is a very fundamental idea, and we want to make sure that we really get it. Okay, so the definition, I'm putting this in quotes because this isn't actually the precise definition of a limit. The precise definition of a limit is a little bit technical. It's not, I wouldn't say it's too difficult for anybody, but we definitely want to get a firm intuition of what a limit actually is before we dive into the technical definition, okay? So I'm just going to give a vague definition. I'm going to say a function f, I forgot to say f, the function f of x has a limit L as x approaches a, which we write with this notation here, this x approaches a. If x gets really, really, really close to a, but not necessarily equal to a, if that forces f of x to become really, really close to L, okay? Again, this is vague, and it's purposefully vague so that we can jump right into looking at limits. Later in the class, I'm going to define what I mean by really, really close. Right now, just looking at a graph or looking at a table of values is going to be enough. Okay? Does anybody have any questions about this non-technical definition of a limit? All right, so if we have this situation where f of x is getting really, really close to some value as x gets really, really close to a, then we write this right here. The limit, this is important, you're going to be writing this a lot. The limit as x approaches a of f of x is L. Okay? So that's what we write if the limit exists. Let me see here. Yeah. If there will be cases where the limit doesn't exist, and we're going to talk about that today, and I'll tell you what to write in that case once we get to it. There's one thing that a lot of calculus students do that it's one of my pet peeves, so I'm going to make sure that none of you do it. But this is what we write if we have a limit, okay? Any questions about this notation at all? All right. So in general, there are 3 ways to find limits. We can find them numerically, which is just with a table of values like we did before. You need to be a little careful with finding limits numerically. I'm not going to show any examples today. I'll show examples tomorrow where using a table of values might mislead you into thinking the limit is one thing when the limit might be something else, okay? Another thing, finding limits numerically, a lot of people, myself included if I'm in a hurry, will, if I'm looking at something like the limit as x approaches 0 of f of x, I want to find this thing. A lot of the times I'll just jump straight ahead to typing in f of 0.000001, and I'll say that's close to my answer. What's the answer? The problem is this, you're only using 1 point, and the limit fundamentally, what's the word I'm looking for? It depends. Thank you everybody. It depends on not just 1 point close to the point you're looking at. It depends on all the points that are close to the point you're looking at. Okay, so numerical limits, that you need to be careful, because this is a thing that depends on really every point that's close to something you care about. And we're only human. Even computers can only calculate a finite number of points. It won't come up very often, but it can trick you sometimes. Okay, so be warned. All right, we can find limits graphically. That's how we're gonna do limits today. In addition to, I'm gonna do one more numerical limit, or two more. But then we're gonna look at some graphical limits, and that's just looking at a graph and saying, look, the limit looks like it's there. And graphically is one of my favorite ways to find limits. And then analytically, and this is, once we really get it going in this class, this is how we're going to find most of our limits. The first two ways are definitely still valid. If I'm ever looking at a limit and I have no idea where to start with evaluating it, drawing a graph or writing out a table of values to get a good guess at what the answer might be is a perfectly valid way to start a problem, okay? So don't let anyone tell you that you have to really get into writing out big, complicated expressions. You can always write out a table of values first to see what's happening, okay? So analytically, we're maybe going to get to that tomorrow, more likely next week, about with evaluating limits analytically. Okay. So let's look at one more numerical limit where the limit does exist. You want to find the limit as x approaches 1 of this quotient, x minus 1 over the square root of x minus 1. So another thing that a lot of people are tempted to do right away, and it's not invalid, is to just plug in x equals 1 into this. The problem is with that is that you have to have a special type of function to be able to do that. We're going to get into that. Those functions are called continuous functions. This function is not continuous, and so we can't just plug in 1 to see what's happening. Because if I plug in 1, what happens? I get 0 in the bottom, but I also get 0 in the top. And so 0 over 0 is what's known as an indeterminate form, and we have no idea how to handle that yet. We'll cover it in this class. So filling out a table of values is a perfectly fine way to find this limit, though. So if anyone has a calculator handy, they can follow along. I did these at home before. 0.9 minus 1 over the square root of 0.9 minus 1. When you round that to 3 decimal places, if I remember right, you get 1.949-ish. If anybody also at home has a calculator, you can check me. Everybody check me. 0.99 minus 1 over the square root of 0.99 minus 1. I believe that's about 1.99. I should have made these boxes bigger for myself. I did not. And then lastly, from the left, we get 0.9 minus 1 divided, sorry, 0.9, no, that was wrong. 0.999 minus 1 divided by the square root of 0.999 minus 1. I think this one's, if I remember right, 1.995-ish. So what does it look like we're approaching from the left? What does it look like the value of this limit is? Yeah, 2. Yeah, exactly. It looks like this is approaching 2. With limits, we need to examine from both sides, because when I said in the vague definition of the limit, really, really close, well, you could get really, really close to x equals 1 from the left, right? And you could also get really, really close from the right. And so if I get one thing coming from the left, if it looks like f is approaching one thing from the left, but another thing from the right, well then f, there's no one value that as I get really close to 1 here, that f is approaching. In this case, there is one value, because as you evaluate the limits from the right, 1.1 minus 1 over square root of 1.1 minus 1 is about 2.0, or no, sorry, I think it was 2.1-ish. Again, check me. These are rounded, obviously. And then you'll also get on the next one, 1.11 minus, or 1.01 minus 1 over the square root of 1.01 minus 1. That one would give you 2.01, and the next one's going to give you about 2.001. And so from both sides, it looks like we're approaching the value of 2. Okay. Are there any questions on this example? It's really just plugging in. One of the most important things for these types of problems is, and I'm not trying to be facetious or anything, is making sure that you type them into the calculator correctly. Because a lot of times people will, oops, I'm going to right here for a second and erase. A lot of times people will type in on the last problem, x minus, they'll do like 1.1 minus 1 divided by, just in their calculator, they won't use any parentheses, divided by square root of 1.1 minus 1. They'll type it in just like that. And the issue with that is your calculator is going to do this first and not what you want, which is this first and then that second and then divide, right? So when you're typing this stuff into your calculators, make sure to use a lot of parentheses to make sure that you're actually making your calculator do what you want it to. I'll say these problems aren't very useful on exams, so that advice is mostly for homework. I'm probably not going to put anything like this on exams. If I do, I'll show you the values, so you don't really need to worry about that on exams. But on homework, make sure you're typing stuff into your calculator correctly. Okay, so let me erase this as we look at our next numerical limit. Does the limit as x approaches 0 of 2 over x exist? And the fact that I phrased it this way should maybe tell you that no, it doesn't. The last one I just asked, what's the value? This one I just say, does it exist? So what do we think off the top of our heads? It seems like no, because the last one, if you just plugged in, quote unquote, you can't actually plug in 1 in this last one because you would get 0 over 0. But if you do just plug in, quote unquote, 1, you get 0 over 0, and in some way, those zeros cancel each other out, right? Here, if I plug in, again, you can't actually plug in 0, but if I plugged in 0 in the bottom, then I'm going to get 2 over 0. There's nothing really to cancel that division by 0. So it seems like our, a guess right off the bat is going to be no, that there's not going to be, thank you, Will, that there's not going to be a limit as x approaches 0. But let's actually verify that for ourselves. So for x equals minus 0.1, because again, we need to look at this from both sides, as x approaches 0 from the left. So 2 over negative 0.1, well, 1 over negative 0.1, that's negative 10, right? So this is negative 20. I think I can actually write that in here if I write small enough. Boom. The next one I won't be able to. 2 over negative 0.01, well, 0.01, the reciprocal of that is 100, right? So this is negative 200. Oh, I can actually say negative 200. Boom. And then 2 over negative 0.001, well, what's that value? Negative 2,000, perfect. You guys can see patterns. Negative 2,000. So even there, it seems like there's not, those values are getting very, very big in the negative direction. Seems like something's fishy. What about from the right? Well, I mean, there's not much difference in approaching from the right other than all these values are positive, right? So I'm going to get positive 20 here, 200 here, and 2,000 here, right? So does it look like I'm approaching a single value, that f is approaching one single value? No, right? It looks like if as I approach from the left, it maybe is approaching some value, but it's definitely negative, right? And it's definitely very big negative. And from the right, it maybe could be a bit, but it's definitely very big positive. So there's no one single number that this function approaches. And this is the fundamental way, one of the fundamental ways in which the limit fails to exist. If I approach one thing from the left, I approach a different thing from the right, then there's no possible way that the function itself can settle down on one number between those two conflicting things. Okay. Any questions on this example? Okay, because it is just as important to recognize when the limit doesn't exist. So in this case, we would write the limit as x approaches 0 of 2 over x. You could write for short DNE for does not exist. Okay? The pet peeve I have, and I know if I tell you, you guys are just going to do it to make me mad. A lot of Calc 1 students will write an equals here. Equals does not exist. That doesn't make sense. Equals does not exist? No, no equals there. So the limit as x approaches 0 of 2 over x does not exist, is how I would say this in plain English. Okay. Any questions? Okay. Moving on to graphical limits. So a graphical limit, we just look at the graph. If I give the graph to you, it might be the case that you have to do the graphing yourself. And in that case, you need to be careful because maybe you're plotting values from a table, and I already told you why that could be dangerous, right? You might be missing something in the gaps. So let's look at just a generic example, but that illustrates exactly what's happening with limits. So I've got some function that's doing something like this, okay? And at the x value 5, this function is actually negative 5, okay? That's how we read this graph. That hole in the middle of the graph there at 5, 5 means that the function's not actually 5 there. You look for the dot, right? So in old classes, in old math classes, when you looked at this graph, the only thing you cared about when you saw this was you know, what is the function value at any point? So if I asked you f of 0, you would say, oh, it looks like it's maybe 3. If I asked you f of, I don't know, -7, you would say, yeah, it looks like it's about 0, right? f of 0 looks like it's about 3. F of -7 looks like it's about 0. And if I ask you what is f of 5, you would rightly tell me f of 5 is -5, right? Because the actual function value there is -5. In calculus, though, we don't care about that when we're evaluating a limit. For the purposes of calculus, when you're evaluating a limit at a point, there might as well be a solid black vertical line there covering up what's actually happening. Okay, I only care what's happening around the point. So now looking at this, with this solid black line covering up what's actually happening at 5, what would you say the limit, this is f of x, by the way, this graph. What would you say the limit as x approaches 5 of f of x is? Well, what does it look like f is approaching?
Negative infinity?
I mean, from the right, it looks like it's approaching what?
Oh,
yeah, it looks like it's approaching that line that, I mean, I'm bad at drawing, but you know what I was trying to get at, right? And as we approach from the left, it looks like it's approaching, yeah, it also looks like it's approaching 5, right? So as I approach from the left, it looks like it's approaching 5. As I approach from the right, it looks like it's approaching 5. So then from our definition of a limit, just what happens as x gets really, really close to 5? The answer is 5, okay? It is not -5, because again, the actual value at x equals 5 does not matter. The fact that f is -5 at x equals 5, I mean, if I ask you what is f of 5, you would say -5. But the limit as x approaches 5, you cover up what's happening at 5 to give yourself a better idea of what's happening around the point. Okay. Before, in old classes, people at home can't see it, but I would cover up the chalkboard with my body, and this is much better to do. Are there any questions about why this limit is +5 and not -5? Any questions at all?
I have a question.
Yeah.
So I know there's terms in calculus where it says like limit of x of 5 as x approaches 5, f of x equals y. When is it y and when is it negative infinity or positive infinity?
Okay, so the question, my speakers aren't working very well. Sorry, the question was, when would the limit be positive or negative infinity? Was that your question?
Yes.
Okay, so if we look back at this example here, or actually I'll just go, I've got another blank graph here. So here, if I draw the graph of y equals, if I draw the graph of y equals 2 over x, it looks like this. It goes like that, and as it gets closer and closer to 0, it goes to positive infinity, right? And as we come at it from the left, it shoots off to negative infinity. Okay. So for this guy, first of all, you'll get a lot of different answers for like, is infinity a good answer to even put down for a limit? Because infinity is not a number. In my definition of limit, I said f of x is approaching one number. So there's not a lot of like debate, but some people just like to say if f of x is blowing up like this, to just say in both cases. Let's look at a slightly different example that would show why we would even consider that. If I have an x squared here, then as we approach, then that just makes this look like this essentially. So now someone might say that, well, that limit I would call positive infinity. And you can do that if you want. If the limit is approaching from both sides positive infinity, if the values are getting arbitrarily large, and we'll talk more about this next week, then you would say the limit as x approaches 0 in this case is positive infinity. Or you could say the limit does not exist. I would be fine with either of those answers. But so this is fundamentally different from this, where this is approaching, even though f of 5 here, because here's 5, f of 5 is down here at -5. Even though f of 5 is -5, you just think of covering up the line. If I'm looking at the limit as x approaches positive 5, you just think of this as, well, I just need to cover up what's actually happening there. Because again, what actually happens at the value doesn't matter. Did that maybe answer the question?
Yeah, thank you. Yes, thanks.
Okay, cool. Yeah, my speakers, I don't know why that's probably me. Who knows? Okay, so any other questions about this? I'm seeing a question about why I marked f of 5 as -5. This is just the way I defined f of x to be. Okay, you're allowed to define any point. As long as the f is only defined as one thing at one point, then it's a perfectly valid definition. Okay. All right, so really quick, I'm going to get into, actually this was very good for when a limit fails to exist, or when you would write the limit as x approaches 0 is positive infinity. We'll get more into infinite limits like this. This is what's called an asymptote, and finding these is going to be probably a good chunk of part of this class when we talk about graphing, because part of this class is going to be about sketching accurate graphs using what you know from calculus. But there's one more example that I think I can get to in the time I have left of a limit that does not exist. So we're going to look at the function y. We're going to look at the function y equals the absolute value of x over x. Okay. So absolute value of x over x. If I start plotting points, I can't plot 0, right? At 0, this is undefined. I can't do 0 over 0. But everywhere else, I can do absolute value of x over x. So what is, if I plugged in x equals 1, what does that look like? Well, the absolute value of 1 is 1, right? So 1's about here. There's 1 over 1. Absolute value, what about 5? Oh, sorry, I marked it at 5. Sorry, guys. 1, 1. What about at x equals 5? The absolute value of x is 5, so I do 5 divided by 5 to give me 1, right? And really, at any point where x is positive, I'm going to get 1 everywhere, right? And so I'm going to get an open circle there because I can't define this at 0. I'm going to get something like that. Ignore how my dots look. What about for x negative? If I plugged in x equals -1, what would I get? Careful. Yeah, the absolute value gives me +1, but then when I divide by -1, I get -1. I'm tricky. So I get -1 down here. I get, if I plugged in -5, I still get, same thing happens, right? So this hopefully is clear. If you plugged in any old negative number, you'd get that positive number over the negative number to give you -1. So I'll draw that like that, and then still not defined at 0. Okay. So I hinted at this before, where if you approach something from the left and you get one value, and you approach from the right and you get another value, then that means the limit doesn't exist. So here, again, if I'm looking at, I need to say what limit I'm looking at. If I'm looking at the limit as x approaches 0 of absolute value of x over x, well, again, whenever you're doing this, whenever you're looking at these limits, cover up the line that you are actually interested in. There's the line x equals 0. I'm covering that up so that the actual value at that point doesn't influence my answer. Okay? So what does it look like? And I'm going to introduce some new notation here, but it means exactly what you think it means. If I look at the limit as x approaches 0 from the left, if I put a little minus on top of the 0, that means as x approaches 0 from the left of absolute value of x over x. What does that equal? -1, perfect. For this problem, you might as well, in addition to covering it up, you might as well zoom in and only look at values to the left of x equals 0, right? Well, clearly that's because this is at -1. Clearly, that's just approaching -1 the whole time, right? So the value as x approaches 0 from the left of absolute value of x over x is -1. All right? And who can guess what the notation is for x approaches 0 from the right? Yeah, I put a little plus sign upstairs on the 0. This means the limit as x approaches 0 from the right. And that means exactly what you think it means. Instead of looking at all the values close to 0, you only look at the values close to 0 on the right. So you might as well just be looking at this part of the graph. And again, this is +1 here. So what does it look like the function is approaching as x goes to 0 from the right? +1, right? It's just staying at +1. You guys are nailing this. So the limit as x approaches 0 from the right of absolute value of x over x is equal to +1. Okay? And so, because these two limits are different, which is something that I mentioned on a previous problem, because those two limits are different, clearly f isn't settling down to one value, right? And for that reason, we would say this top limit here, the limit as x approaches 0 of absolute value of x over x, does not exist. Not equals does not exist, but just does not exist. Okay? Any questions on this one? I got a chat. I'll answer your question, Saba, in a minute. Any questions on anything we covered today? There's one more example that I'm going to show you tomorrow where a function fails to have a limit that's fundamentally different from the last two examples that I showed you. It still has to do with all of the ways that a function fails to have a limit. It's just that the function it never settles down to one value. That's the whole idea. But it's a little more complicated. So I'm going to save it for tomorrow. Did this work out? I'm new here, guys. So if anything I do is stupid, let me know. But was this good for everybody here and at home? Hopefully. Okay. If not, let me know and I'll change things. Leave your names where you're sitting currently so I can write them down. And remember where you're sitting, hopefully. I'm going to write it down in a seating chart that I can always tell you, but leave your names where you're sitting currently, please. All right, if there's no questions, If you do have questions, you can always come. I'm going to be free after 1:45. So you can always stop by my office from 2 to 5, and I'll be in there unless I'm getting coffee or something. Okay? All right. Thanks, guys.
Thank you.
Mm-hmm. Okay. Online, do we have? Let me check if I've got any. I'm going to stop this recording.